só de atraso. E vamos começar então a sessão da tarde. Nós teremos então o curso do professor Rangayyan. Sobre análise de textura, né, de formas. Vou pegar aqui. Análise de formas, textura e orientação de padrões em imagens médicas. Então, nós temos aí a previsão, acredito até 5h30, 6 horas da tarde, e vai ser uma boa pisada para o professor.
Thank you. Boa tarde. I will have many equations and figures. If you find it difficult to read from the back, feel free to come to the front. With the projector, it is a little difficult. Some figures may not be clear. PDF files of this are on my website. You may download them. So I would like to thank the organizers for inviting me to come here and make these presentations. The seminar I gave in the morning was on our research project related to computer-aided diagnosis of breast cancer. Now, there are two parts, well, the whole afternoon with a coffee break, where I will present lecture material, tutorial material on analysis of shape and analysis of texture, including oriented texture. At the University of Calgary, I teach a course on digital image processing. And this course is for about 13 weeks, about 40 hours of lectures. These topics are a part of the course. I have a book on biomedical image analysis, and this is chapter 6. So these lecture notes are related to my book and my course. So please excuse me for jumping abruptly into chapter 6. But the previous chapters deal with pre-processing of images, removal of noise, filtering for enhancement, detection of regions of interest, transformation techniques, like what you have heard so far. And again, Professor Leticia Hittner mentioned these topics yesterday. This is afterwards. There was an interesting distinction made between image processing and image analysis. And I say the exact same thing to my students also. The initial stages of analysis of imaging and image processing start with image acquisition, just measurement, data acquisition. Then removal of noise, enhancement, segmentation, they are all pre-processing steps. After segmentation, you begin with analysis. When you filter an image, the result is an image. When you enhance an image, the result is an image. You may want to make the image look cleaner, better, sharper, prettier, whatever. But the result is another image. But when you perform segmentation or detection of an object or region of interest, the result is not an image anymore. It is a part of an image. It may be only the contour of a region or an object or a tumor. Then, the next step is analysis. How do you analyze this part of the image that you cut from another image that you started with? What are the important features or attributes or descriptors for the application? Of course, this depends on the application. This depends on what is the purpose of this investigation and what are the types of objects you have and how many classes, how many groups you want to separate them into, and what are the distinguishing or discriminating attributes between these groups. So all of this is prior knowledge of the domain of application. As an electrical engineer, I don't know all of that in medicine. So I collaborate with a radiologist, with a nuclear medicine specialist, with an ophthalmologist, with a dermatologist, and so on. And from them, we get the domain knowledge. What is the difference between a malignant tumor and a benign mass in the breast in the case of mammography? What is the difference between a lesion that has healed and a lesion that is not healing well? What is the difference between a lesion that is responding well to treatment and one that is not responding well to treatment? So all of this domain-specific information or knowledge is the expertise of the person in that domain. So by collaborating, we get that information. And then we can develop quantitative methods for objective analysis. This is what Dr. Paolo Mazzanzini, as a Marcus, explained to you. We want objective analysis using quantitative measures derived from the features. Whereas a medical specialist will look at the image and say, here is a tumor, it looks like it is malignant. No measurement done, no boundary drawn. So it is an opinion, it is very important, but it is based on visual analysis and subjective analysis, but with substantial training. When you want to do this using scientific methods, engineering methods, using computers, we must first extract attributes or measures, features from each of these regions. In many applications, the features that are important include shape and texture of form, variation of the form, and variation in the color or gray level or intensity or density or temperature, whatever the pixel values represent. So in this afternoon's tutorial, we will start with shape. I will go through this in full detail like what I do in Calgary in my course. The texture part is very big, chapter 7 and 8 in my book and also in my lecture notes. Lecture notes in this format are available on my website for chapters 1 through 8 of my textbook. But for texture, I will give you just a sample, a condensed version, because that topic is much bigger than what I can do in 1 or 2 or 3 hours. So analysis of shape is something that can find application in many different areas, and some of these methods are fairly general, some are specific, as you will see, and I hope you will find this useful and interesting. And again, if you find it difficult to read the details or see the pictures, please come to the front. So, to begin with, in biomedical applications, we know, even if we are not studying medicine, that several human organs possess readily identifiable shapes. The shape of the heart is well known. It's not this shape that we write in greeting cards or when sending messages. The shape of the heart is not that, although it is called a cardioid shape. But we know the shape of the heart. We saw in Dr. Leticia's presentation the picture of the heart. The brain, if somebody draws a sketch like this, you say it is a brain. If somebody draws like this, you say it's kidney. Or you may say it is a bean, but kidney is supposed to have bean shape, or beans have kidney shapes, depending on which way you cut. There are beans called kidney beans, so I don't know what to say. So kidney has bean shape and beans have kidney shapes. So heart, brain, kidneys, even the bones, the long bones, they have very specific shapes, and their shapes are almost the same for all of us in general. There is an average shape for human beings of these organs and parts of the body. But disease processes can affect the structure of organs. The disease process may be having a local effect, but eventually there is some structural damage that is done and can cause deviation from the expected or average shape. The heart can become expanded or enlarged. The left ventricle could become bigger. If there is a tumor, there will be some change in even the external appearance of a certain part of the body. So shape factors could be, appearance could be modified by disease processes. Even abnormal entities have some shape characteristics. Masses and calcifications in the breast. There is a difference between calcification due to benign disease and due to malignant disease or cancer. The same with a mass or a tumor. A mass due to a benign disease is usually round, oval, compact, whereas a mass that is spreading, metastasizing due to cancer will have many finger-like protrusions, what are called spiculations, because it is spreading and affecting the neighboring tissues. So even abnormal entities have some shape characteristics and differences that are worth noting, and I'll show some examples. So most benign masses in the breast appear as well circumscribed areas, compact. You can draw the boundary easily. Even you can and I can draw the boundary. A radiologist can do it very easily. Some benign masses may be macrolobulated. Instead of being compact like an oval or circle, they may have a little lobulation. Maybe 3 big lobules. Malignant or cancerous tumors are typically ill-defined. The boundary is difficult to see because of the spreading of the disease. The disease is affecting the neighboring areas and possess rough or stellate or spiculating shapes. Instead of being compact, the tumor is now having many fingers protruding in different directions. Or they may be microlobulated, little lobulations, many little lobulations. The boundary is rough, whereas for benign mass it is smooth. So this is an important distinction, and this is true and has been observed in various parts of the body, in 2D, in 3 dimensions, it doesn't matter, in the brain, in the kidney, whatever. Because the basic malignant process is metastasizing and spreading. A benign mass is contained, almost encapsulated. But there are some problems, especially in mammography, because of the fact that it is a projection image. The 3-dimensional breast is compressed and radiation is sent through in one direction, craniocaudal, and another direction, usually mediolateral from the middle to the side. So multiple planes in the breast will be projected and integrated onto the plane of the image. So there could be a benign tumor here, a benign mass here, and there could be some structure, a ligament here, and a benign mass here, and a vessel here, when they superimpose, may look like a spiculated tumor, which is only a false appearance because of the projection. So the geometry of the projection also matters. A tumor may have many spicules this way, but if you project in this direction, all the spicules will be integrated. So the way the tumor is projected is also could cause some misleading information. So projection, superimposition of multiple objects, and they can modify the shape of the appearance, the object as it appears in the image. A trained radiologist can separate. This is the mass, this is a ligament behind the mass or in front of the mass. They are not connected. But for a computer algorithm or for an engineer like me, it will not be easy. So let us see. Sometimes computer methods and analysis by those who don't know the details may lead to results that are not perfect. But nobody is perfect. Radiologists are not perfect, pathologists are not perfect, no procedure is perfect. You may do a biopsy by putting a needle, and the needle may not go through the tumor. It may go there by mistake. So then the whole result is wrong. So it is good to have multiple methods of analysis and build robustness into the procedure of analysis so that it can be tolerant to errors and misleading or missing data. So let us look at some methods to represent shapes and contours. In computational representation, a shape or an object is represented only by its contour in terms of the x and y coordinates, just the points of the pixels along the boundary. And you may write this as xn, yn, n going 0 to 1, 2, 3, n minus 1. There are n points on the boundary, so you write xn, yn, that's the contour. There is no gray level or intensity value along the boundary, it is ignored. And a contour may be shown as a binary or a bi-level image for graphical representation. Sometimes it is convenient to convert the two-dimensional representation into a one-dimensional representation called a signature. For every point on the contour, you may derive some property of the contour or the object and plot it as a measure of how you go around the contour. And then it is called a signature. So you essentially reduce the dimensionality from 2 to 1. And it may facilitate analysis of the information from a different perspective. What is the reference for this? Usually the center of mass or the centroid of the contour, the average of the x and y coordinates. So x bar is the average of all the x coordinates and y bar is the average of all the y coordinates, and that gives you the centroid. And you can take the distance from the centroid to every contour pixel, xn minus x bar square, yn minus y bar square root, Euclidean distance, dn. Now the contour is represented using a one-dimensional signal, dn, for all n. So you can plot it like a one-dimensional signal. You can do Fourier transform analysis, like what Dr. Leticia showed. Dr. Maiza showed this morning. So centroids of regions can represent useful information sometimes. But sometimes the centroid may be outside the object and it may not have any meaning because it is not a physical point within the object. For example, if you have a crescent moon-shaped object, the centroid is outside, which means there is no point on the object that can support it in a stable way. So then, do you want to use that as a reference? I don't know. So there is a question mark. You can also take the radial distance signature. There is a contour. From the centroid, you draw a horizontal line and sweep. For various angles, from 0 to 360 degrees, you draw lines and measure the distance to the contour. And then you get a signature that is a function of the angle 0 to 360 degrees with the centroid as the reference. But the problem is sometimes the contours may have many spicules and a rough shape. When you draw one line, it might intersect the contour many times. Then what do you do? Again, I don't know. There is no simple answer. So some of these methods have limitations. But still, we can analyze them, understanding that there are these possible situations. So for irregular contours, a signature using angle way of scanning, we have multi-valued points. So then you have to make a decision what to do with that. One important point, going around the contour more than once will give you the same thing. Go around and measure dn, get the same thing. So it is a periodic signal. So if you're doing signal processing, you know that periodic signals can be represented using the Fourier series. And the interpretation of the spectrum is different in terms of harmonics. So the signature is periodic with the period equal to n, the number of points on the contour. So here is a graphical illustration. This is some shape, could be a benign mass, centroid, and you go around, and this is D0, D1, D2, go all the way around. This is the radial distance from the centroid to the contour as a function of angle, 0 to 360 degrees, or reference could be anything, it doesn't matter. Or you can take all these points, Z0, X0 plus JY0, this point on the contour. The coordinates are X0, Y0. Put that as a complex quantity. Engineers like to make things more complex than they are. This is a real world, X and Y are real, but by putting this as a complex quantity, there are some advantages when you go to the Fourier descriptors, which Dr. Paulo mentioned earlier. I'll go into that in more detail. So Z1 is X1 plus JY1, so on, go around. Now you have a complex signal, Zn. You go around, you get the same thing. So you don't have to go around more than once, but if you do, it is periodic. This is where there are some difficulties in projection. Please download this file and take a look later if you want. This is the contour of a benign mass in a mammogram, drawn by Dr. Deserter, a radiologist specializing in breast cancer. So it is a smooth contour, maybe 1, 2 lobules. This is the centroid, computed. Can you see this at the back? So, can you see this? Okay, so when you go around the contour and get this distance, this is the signature, the DN signature. In this contour, there are 768 points. This was done on mammograms, digitized to a resolution of 50 micrometers per pixel. So, this is smooth signal compared to this, which is the contour of a very speculated malignant tumor, and the signature is very rough. By the way, this is not an ergonomic design. The laser button and the forward back buttons are all very close, and my thumb is too big. So please bear with me. So that is what a signature is. So a contour, very rough, speculated. When I say finger, this is one finger, other finger, multiple fingers. And smooth, macro-lobulated, benign, smooth contour, smooth signature, simple signal. Malignant contour, many spicules, rough contour, rough signature. In one period of the signal. The period may be different, it doesn't matter, you can normalize. But in one period, it's having more oscillations than the other one. So this is rough, high frequency. So if you want to do analysis in one dimension using traditional signal processing techniques, use this. If you like 2 dimensions, do this. Of course, you can do this in 3D if you can get the boundary in 3D. And one of my students in India has done that for lung nodules. For computational purposes, you may also represent a contour using a code and reduce the dimensionality and the memory requirement of storing. The reduction in memory requirement is not important. Nowadays, computers have a lot of memory. But chain coding facilitates the analysis of the contour. So this was proposed by Freeman many years ago, more than 50 years ago. So you start at one point on the contour and go around, but you don't go around in a continuous space, you go in a discrete space, pixel to pixel. You can only go horizontally or vertically. or we can go horizontal, vertical, left, right, top, bottom, and diagonal. And each movement is given a certain code. Let me show this first and then I'll go. If you allow only 0, 1, 2, 3, 4 possibilities of movement, to the left, to the right, to the top and bottom, you get this code. If you allow the diagonal, then you go 0, 1, 2, 3, 4, 7. This requires 2 bits per step. This requires 3 bits per step. So you give the exact coordinate of the starting point, and for the remainder, let me show this example and I'll come back. For the remainder, you just give the code. So this is the starting point. You go 0, 1, 0, 3, 3, 0, 0, so on. The actual contour may be some shape like that. But this is the Freeman chain code, and the chain code is this. So you give the coordinates of this point and this, and you can draw this contour on a discrete grid. If you allow diagonal movements, then the same contour may look like this: 0, 1, 6, 6, 0, 7, 4. Some more details, a little more sharper detail, a representation of the actual contour, which may be like that. So what is the advantage? I will mention a few. The code is invariant to shift or translation because the starting point is kept out of the code. It is almost invariant to size, but you can scale the result, and you can plot the result to different size if you want in a very easy manner. Contours of different sizes may be generated from the same code by using different sampling grid. One step. How big is a step? It can be a little step, it can be a big step. So you can reproduce the same shape approximately to different scales. You can enlarge by a factor of n by repeating each code n times. You can also shrink, reduce the size by reducing the code elements to single numbers with approximation of unequal pairs by their averages. You take 2 values and average them, and next 2 values and average them, and give only the average. So the size of the code is reduced by 50%. You can normalize for rotation by taking the difference. Take the difference between successive codes and add 4 or 8 to the negative differences, then the result is invariant to rotation of the object. Using an 8-symbol code, you can rotate the contour in steps of 90 degrees by adding 2n to each code element and do integer division by 8. So those of you who are in computer science will easily understand these things. Engineers, we have to think a little bit more. The addition of an odd number rotates the contour by 45 degrees. So the chain code is not simply useful in representing a contour, but also in the manipulation and analysis of the result. The length of the contour is the sum of all the even parts and add all the odd parts, but multiply the odd parts by √2. Diagonal connections are multiplied by √2 using the 8-symbol code. You can also achieve reduction, check for looping, determine the area. There are many procedures. So using this code or this code, you can compute many parameters related to this object. And this was proposed by Freeman about 50 years ago. So that is one basic representation and a little bit of analysis of contours. Now let's see how we can break a contour into parts. The contour of a tumor could be very complicated, and you may want to separate into parts, each spicule, each lobule separated. And you can do that by finding what are called points of inflection, where the curvature changes. For this, you need to get the derivative. If you have a function fx, let f prime x be the first derivative, double prime the second derivative, triple prime the third derivative. In the coordinates of the contour, you have x and y coordinates. Treat them separately, and then you take the derivatives. To find a point of inflection, the conditions are the second derivative must be 0, the first derivative is not 0, the product of the first and second is equal to 0, and the product of the first and third derivative is not 0 for each x and y functions. You can write this in complex form by letting bold C be equal to x and y, then C prime cross C double prime must be 0, C prime cross C triple prime must not be 0. So this gives you a set of equations. And these equations are like this in terms of the derivatives of the x and y coordinates. So by solving for this set of equations, you can find the points of inflection that can help you break a given rough contour into parts that you can analyze in detail. Now, computing the derivatives is difficult, not computationally difficult, but the result you get will be noisy. If there are errors in drawing the contour manually, sometimes there is a little bit of tremor when the pixel size is 50 micrometers. When you are tracing on a big monitor or graphic tablet, or when you have a computer method, an algorithm to detect the boundary, it will be affected by noise. There will be some artifacts. So when you take the derivative, first derivative, second derivative, third derivative, the noise will be amplified. So you must build some filters to smooth these results. Otherwise, you will find many points of inflection. So one of my students, Minute, worked on this, and the problem was false or irrelevant points of inflection. There could be many points of inflection, and they are not important. I'll show some examples in a moment. So when you get the derivative, you don't simply take xn minus 1. You take a number of differences, xn plus I minus xn minus I going 1 to m divided by I. This is the average derivative using m points. So it's like a filter you are running around the contour and averaging the derivative. And then you take the derivative of this, then you take the derivative of that, because you need first, second, third derivatives. So I'll show the result here. This is the contour of a malignant tumor in a mammogram drawn by the radiologist. And the contour has several hundred points. I don't remember how many. The number of points of inflections is 58. These are all points of inflection. So how do you analyze this? This is one portion. This is convex, pointing out. This is another portion. Looks like it is a straight line, but it is actually concave. This is convex, concave, convex, concave. This is concave for sure. Concave, convex, concave, convex. This is almost straight, but it is concave. Now there are more points of inflection than we need. I was hoping this would be one part. All of this is another part like this. But I don't want this, I don't want these. I wanted all of this to be one. But this is what we get with an automatic procedure. If you want, you can go and modify it. But it looks good. This is one part, this is another part. Lobule, one lobule, another. Very clear. Convex, concave, convex, concave. Beautiful. Automatic. The number of inflection points detected depends on the filter or smoothing that we use. If we don't use any filters, we get 1,200 points of inflection. Any little variation. By smoothing, we reduce it to 58. And we track this, and when there is not a large change, we say this is where we stop. So it is an iterative procedure if you want to find it, or you can say smooth so much and take the result. So you must be careful, otherwise you get a large number of points of inflection. So when you put this on the mammogram, this is on the mammogram, there is a tumor here. This is the boundary drawn by the radiologist, and here we have convex parts in white concave parts in black. I should have used color, but in this I don't have color. I hope you can see the black and white parts. So this gives an idea. This is what Dr. Desater told us. He said, if the mass is benign, it is a convex object, a circle or oval, not square. Usually as oval, like an egg. No concavity, no points of inflection, one smooth curve. Of course, there will be some noise, some inflection, so there will be some, in a real contour of a real benign mass, there will be a few breaking points. But a malignant tumor will have many concave parts. A benign mass has no concave parts. So here, concave, concave. This, I don't know, it's almost straight. Concave. So by breaking the contour into parts, we took the total length of the concave portion, all the black portions, divide by the total perimeter, and we call it fractional concavity. And you can do this in 3D also. And in this case, fractional concavity is 0.47. 47% of the contour is concave. This is a benign mass. 1, 2, 3 lobules, macro-lobulated. This is concave, concave, concave. Saying that, I don't know, a little piece there. So there is a little bit of concavity, but mainly convex. Fractional concavity is 0.16. So this is a good discriminating feature based on the observation of the radiologist and the characteristics of benign masses versus malignant tumors. And this is a good shape factor that we have used to discriminate between benign masses and malignant tumors in mammograms. Okay? Now, when you have contours that are drawn by hand, there could be some tremor or some noise. And when you obtain by computational methods, there could be some artifacts. So it is good to apply a model and remove irrelevant detail. So very fine details like this may be replaced by a straight line. So for that, we can apply a procedure called polygonal modeling that was originally proposed by Pavlidis and Horowitz and Pavlidis and Ali, and there are some algorithms by Ventura and Chen. And we have modified one of their algorithms to get better results. The algorithm, let me show the picture first and then I'll come to the algorithm. So here is the contour. The original algorithms proposed by Ventura and Chen said you start from multiple points and see how the algorithm converges. The question is how many points, what is the first polygon I should put? You can use a bounding box, but it must be inside most of the time. So we said no, we already have the points of inflection. We will join the points of inflection and make an initial polygon. So these are all the points of inflection and connect them, you get a polygon. In this case, 58. 58 points, 57 sides. Now, then you ask the question, is this good? Are you happy? Well, I'm happy here. It's straight, I'm happy there, but I'm not happy here, I'm not happy there. This polygon is going like this and there is so much of the contour left outside. So then ask the question, how much is that? What is the distance between one side of the polygon, the chord joining this point, and what is the arc length? And what is the distance between this and this line and the arc? Maximum distance. So find the maximum distance between this side and the remaining part of the contour, the original contour. If that is more than some limit, whatever you say, 100 micrometers, we said 100 micrometers because 1 pixel is 50 micrometers. We said we will allow a variation of 2 pixels. If it is more, then you take the distance of the point on the contour with the maximum distance and include that as a new vertex. So now, sorry. You include one more point and then the polygon goes like that. And iterate. Keep iterating that until there is no more change. And the final polygon is shown here, which is almost the same as the contour. The contour had several thousand points. There are 146 sides to this polygon. So you have reduced the number of points on the contour. That's not our aim. But you can approximate this very rough contour using a polygon with only 146 sides. It's a geometric shape, so you can analyze using any geometrical method you want. So for this, the algorithm, so each curved part is represented by some SC and K. You find the maximum arc to chord deviation. If the distance is between, if it is more than 0.25 millimeter, 5 pixels in our case, the curved part is segmented at the point of maximum deviation and be joined by a straight line. If it is between 0.1 millimeter and 0.25 millimeter, it is segmented at the point of maximum deviation. But we also said each side of the polygon must be at least 1 millimeter. So you can put conditions as required. You don't want sides of the polygon being very small, 1 pixel. You say minimum 1 millimeter, and so on. These are particular to the application, so you don't have to be concerned much about that, and iterate. Iterate this until there are no more new vertices added to the polygon. And the result is this. So in the case of here, the iterative procedure starts with 58 points and saturated or converged at 146 in 5 iterations. So it is fast. In the case of a benign mass, these are the points of inflection I showed earlier, and this is the final result with here there were 14 sides and here 36 sides. So this is a polygonal model. What do you do with this? It's up to you, but I'll show an application to get a method, get a measure of speculation later on. We can also use this to analyze concavity. It is easier to use the polygonal model, and then you will reduce points of inflection along these sides because you are approximating many variations here with a straight line. So points of small curvature can be ignored. Then I had Olivier Menut, I mentioned his name earlier. He came from France and said, I don't like polygonal modeling. He said, why polygon? Contours of breast tumors are not made of straight lines. So he said, let's do parabolic modeling. So we said, okay, now take the same thing, segment the contour first, take each piece and fit a parabola. But there are problems because these parabolas are like this and like that and like this and like that. So you need a geometric transformation. Take all those pieces after finding the points of inflection, put them all, do a geometric transformation, put them all on the x-axis and fit parabolas. Get the width, get the parameter of the parabola and use the statistics of those for classification. So for this, we said x, s, y, s are the contour pixels, coordinates, as you go around the contour. Sometimes this representation is used. Instead of pixels, you say the total length of the contour is equal to 1. If you go on the contour, it is going 0 to 1. What is the step? Up to you. So you traverse the contour using this variable s, which is the step size, as you go around the contour. And give the x and y coordinates for each step, whatever the step size. So you have more control on your procedure, not limited to the pixels. Y equal to ax squared is the equation for a parabola, as you know, and a is the openness of the parabola. That's the parameter we want. Larger the value of a, narrower is the parabola. Why do we want parabolas? When there are spicules, they are very narrow. When a tumor or a benign mass has macrolobulation, it is a broad parabola. So if there is a parabolic segment that is having value of A that is large, it is a narrow spicule. So how many narrow spicules do you have? Check A after parabolic modeling. So there are some geometric transformation equations. I'll just mention these. You may read these later on yourself. So rotate all of the parabolas to be on the horizontal axis. So this is the equation for rotation and displacement. Find these parameters theta and C and D. And for this there is a little bit of, I won't read all of this, you can do this later if you wish. And in the rotated coordinate system, x-axis is S, y-axis is A squared. So we want this value of A for each segment of the contour. So you take the derivative and solve for this, and you can find all of this. I'll skip these details, and you get the value of this A. So 2A cos theta is that. So you need the derivatives of x and y again. So solve for all of this. So 2A cos theta is y double prime s, and you got the parameters. So after segmentation of the contour into parts, concave and convex parts, using the points of inflection, each part is modeled this way. You get A. You don't need theta. Theta is not necessary when it is fixed. We're not reconstructing contour. We just want to know how many pieces and what is the value of A for each piece. If there are many pieces with large value of A, it's highly speculated. So we get all the values of A for all the segments and analyze the statistics, mean, standard deviation, and so on. So malignant tumors with narrow spicules or microlobulation should have several segments with large A. Benign masses that are oval, macrolobulated, should have a small number of segments with small A. So large standard deviation for malignant tumors than for benign masses because there is substantial variation. We also use the width by projecting the parabola onto the x-axis. And if the spicule is narrow, the width is small. If it is a broad macrolobulated, it's not a spicule, but we'll call everything as a spicule. A big lobule, the projection is big. So these are features that we can use for classification. Now I won't go through all the details of the application because this is a tutorial, not a research paper. So we got 76% accuracy with 54 contours of benign masses and malignant tumors using the statistics of A and the projection onto the x-axis. It's not very good. 76% is not satisfactory for a clinical application, but these are good features. When you combine with other features, you get better results. If you take 3, 4 features, each one giving 76%, 75%, 70%, put them all together and hopefully they are complementary, the net result may be 95%. Okay? Just one moment, please. Yeah, holding the microphone, I only had one hand free. The methods I've mentioned so far are useful when you have a closed contour, an object that has a boundary and you have the full contour of the object, what is called a closed contour. But sometimes there are objects that are branching patterns, like a tree, like the vascular tree, the main bronchial tube and then the branches. There is no closed loop, there are branching patterns. How do you analyze that? Then you need the skeleton of the object. To get the skeleton, first you have to detect the object, maybe in 2 dimensions, let's say. Detect the tree of blood vessels or airway, binarize, remove small pieces that are not important or artifacts, and then reduce that if the thickness is not important, or even if thickness is important. First, reduce the pattern to a skeleton, just the center line, or a skeleton, a line, 1 pixel thick line showing the full pattern. And then you can go back and measure the angle, the thickness at every pixel, every point on the skeleton. So objects that are linear or varying, curvilinear, not closed, branching patterns may be analyzed by their skeletons. The skeleton is obtained by what is called the medial axis transform, or a thinning algorithm. The medial axis transformation proposed by Bloom says the image is binarized first. You are detecting the object. So if the binary pattern is B, let C be a set of contour pixels of B, and let Ci be 1 point on the contour. If a point is on the contour, you want to remove it. If it is in the middle, in the inside of the object, you want to keep it. That's the general idea. So for each point B in that object, a point Ci is found that the distance between B and Ci, BBCI, is at the minimum. And then if there is another point with the same distance, then this point is in the middle, approximately the middle of the object. Then you keep that. B is part of the skeleton, otherwise it is not. Now this is the theoretical definition, but it's not efficient to implement it this way. In practical implementation, there are what are called thinning algorithms. You start with something thick, and it could be, I don't have anything here, it could be a thick line. You will just represent it by one thin line. Remove points on the outside. So a contour point is defined as any pixel having a value of 1 and at least one 8-connected neighbor that is 0 on the outside. And let this be the way of indexing P1, 2, 3, 4, 5, 6, 7, 8, 9 in a 3x3 neighborhood when you are processing P1. Then there are some conditions. Look for combinations of pixels. 2, 4, 6, if any one of them is 0. 4, 6, 8, if any one of them is 0. SP1 must be equal to 1. SP1 is a number of 0 to 1 transitions when you go around. You go around this pixel and check the neighbors. And the number of NP1 is the number of non-zero neighbors of P1 must be between 2 and 6. If these conditions are met, you must delete this pixel. It is on the outside. But you don't delete now, you flag for deletion and go around the whole contour and then delete all the flagged pixels. And repeat by using this combination, 2, 4, 8. So you are asking this, 2, 4, 8 is this. So in this manner you check for combinations. And if these conditions are met, the pixel must be deleted. Delete all of them. Iterate. Keep repeating, and finally you end up with a skeleton. So this is an image of blood vessels in the ligament of a rabbit. Black India ink was injected, so you can see it in a microscope image. The ligament was then taken out and sectioned in a microtome. We were studying the architecture of blood vessels in ligaments. So this is a two-dimensional map of one section, and we have multiple sections. So we wanted to analyze the thickness of the blood vessels and the orientation. In a normal ligament, most blood vessels are straight along the axis of the ligament. When the ligament is ruptured, there are more blood vessels formed. In a normal ligament, there are not many blood vessels. It is avascular. When the ligament is injured, new blood vessels are created to help the recovery process, healing process. And after the healing process, the blood vessels diminish. So we wanted to study that pattern. So this is an image. We wanted to study the orientation pattern, the angle at every pixel, the thickness at every pixel. How do you define a pixel? So you need the skeleton. This is the skeleton by thinning. So all vessels are replaced by 1 pixel thick line regardless of thickness. If you want to measure thickness, go back. Take this, draw a perpendicular line at every pixel until it meets the ends, and measure the thickness here, and measure at every pixel. We did that. Got the statistics of thickness. The orientation, it's the slope of this line at every pixel. It is hard to measure the orientation here, whereas here you can easily estimate the local orientation by fitting a straight line, not to 1 pixel, but a few pixels in a little window, and find the orientation at every pixel. So we got some statistics of orientation and statistics of thickness. I'm not going to talk about that here. It's not part of shape analysis anymore, but this can facilitate further analysis. So this is also analysis of shape. You can do more, but the shape of this is all of this. It is not a closed contour. You cannot define a shape factor, but the skeleton represents the shape. So the next topic is shape factor. You have already seen some shape factors in the previous seminars. Shape factors are measures or attributes that characterize the shape of an object. They are not unique in the sense you cannot say there is only one object that has this shape number, 2.5. There could be many objects that have the same number, but the number for a given object is unique. But the idea of shape, and especially shape complexity, varies from one application to another, from view to view to view. You may say this is smooth, this is rough, but that opinion varies from one person to another, and also one application to another. So in order to represent objects in terms of their contours and shape factors, we need many shape factors, many measures from different perspectives. When you put them all together as a set, you get a good, robust representation. Any one measure may not be enough because it is very specific and has only one idea of shape. So we need several ideas of what is important in a shape, and what is a simple shape, what is a smooth shape, what is a rough shape, what is a complex shape. So the nature of the contour to be encapsulated varies from one application to another. That's very important. But if we know 100 measures, then we can address many applications. If I know only one measure, then it may be good for only one application. Regardless of the application, there are some important requirements which you heard earlier. Invariance to shift in spatial position. Whether the shape is here or here or here or here, shape factor must be the same. Invariance to rotation, whether it is like this or like that, it should be the same. But if I go like this, because of the projection, the shape is different. We will not consider that. We will consider only shift and rotation in the plane of the contour. Invariance to scaling, whether it's this or go close and make it big or small, it should be the same. In most applications, this is enough. In some, invariance to reflection may also be important. But if you're doing character recognition, you don't want that, at least for English. There are other languages, other scripts that are more complicated. In English, P, D, where is B? D, B, B. They are just reflected, rotated versions. So you have to be careful, depending on the application. So these shape factors, or shape factors that meet these conditions, are called invariant shape factors. I find that terminology to be poor, because you have to specify invariant to what? Invariant to this. If it is invariant to benign disease and malignant disease and normal patient, it is useless. So when you say invariant shape factor, invariant to what? Must be specified. Hopefully they are variant with diseases. basic measures, you have heard of them. Fit an ellipse or a rectangle, a bounding box, or the best fitting ellipse. Now, how do you find that is another question. Once you find the bounding box is not a problem, get the maximum x and y coordinates. And get the width and the height, take the ratio. So if it is a square object like this, then the ratio is small. If it is a long object like this, the ratio is larger. So if it becomes a stretched object, the ratio becomes larger and larger. Whether you fit an ellipse or a rectangle, it doesn't matter, then you just take the ratio. So this is called eccentricity or elongation. So if it is a compact, or what would be compact? If it is a square object or a stretched object, you can distinguish between them. It is also referred to as deviation from a circle. For a circle or a square, the ratio is 1. Another measure that is very commonly used in many applications is compactness. Compactness is defined in a few different ways, but the most common definition is P squared over A. P is perimeter or length of the contour, and A is the area inside the contour. It's very simple, but it works in many applications, as I'll show you. The idea here is that when you are given a certain length, what is the shape that you can form to contain maximum area? If area is very large for fixed P, this number is small. As area becomes small for the same P, this becomes bigger and bigger. So the basic idea is this. Suppose I give you this string. The best shape you can make to contain maximal area is a circle. I can't make a circle. And a square, not so much. And if I make a rectangle, the area is reducing. The total length is the same. And if I make a very thin rectangle, the area is almost 0. The perimeter is the same. So the ratio depends on this complexity in a way. What is complexity? What is the area inside the contour? And if I make a speculated object like this, the area will be smaller and smaller, more spicules with the same total length. The area is smaller. So you can say compactness is shown is maximum for a circle, and you can compute that. The perimeter is 2 pi times radius, so 4 pi square radius square. Area is pi r square, so calculate that. R goes away. So this is a dimensionless quantity, r square here, r square here. So what was that? 4 pi square divided by pi, so it is 4 pi. So that is the compactness for a circle, no matter what the size. Of course, you can rotate it, doesn't matter. You can put the circle anywhere. It is invariant to many things, including reflection. So it's a useful shape factor. So the circle is said to be the most efficient shape, in the sense that for a given perimeter, it will contain the maximum possible area of all possible shapes you can create. A circle is round, and when a person becomes round, the person is said to be out of shape. They say you're in bad shape. But that is wrong, because circle is the most efficient space, shape.
I'll go tell my husband that. He's on the job.
So being round is the most efficient shape. I can normalize that. 1 minus 4 pi a divided by p square. So this is better. It is limited to the range 0 to 1. When this is 0, when p is very large, a is very small, goes to 0, 1. And for a circle, this is 1, so this is 0. The total shape factor is 0 for a circle. 1 when either area is 0 or perimeter is infinity. Within practical limitations. So this is advantageous, whereas this, as area becomes smaller and smaller, this becomes very big. It is positive, non-negative quantity. 0, a case that is not important. It doesn't go to infinity, area doesn't become 0 in a practical application. Although, if you just make a straight line, the area is 0. So it is advantageous, we heard earlier, when you normalize features to the range 0 to 1. Design your parameters so that they are in a certain range, 0 to 1, plus minus 1. When you normalize inherently, it is convenient in pattern classification and also easier to understand. So here are some examples. A circle, CO is 12.574 pi, CF is 0, square 16 or 0.21, any square, any size. Rectangle, it depends. Longer rectangle has higher shape factors. Triangle, higher.
How do you call CF is complexity, or is there
It is still compactness, just normalize.
Okay, there's no specific name.
I have not seen any name, and I don't know if anybody else has used this. We have used it, perhaps others have used it, but this is just normalized compact, same compactness. It is just this way. So we just call it normalized compactness. So the advantage is 0 to 1, whereas the other it goes 12.57 to some large number. Is this rougher than that? I don't know. Depends on how you think. Is this rougher than this? I think everybody will say yes. Is this rougher than that? Yeah. But between the two, I can't say. So you have to create test patterns in each application that are relevant to the application and show the objects to the domain expert and get them ranked and evaluate if your shape measure is suitable or not. For that, we created some test patterns. We created these digitally. So these circles are not perfect circles. They are pixelated circles. And we rotated squares and rectangles and triangles, equilateral triangle and right angle triangle. So we created these shapes. The expectation is the shape factor should be the same for all of them. Not all of them this way, but this way, in a row. All of these should have the same number. All of these, maybe. All of these, perhaps. So we don't have to read this. We computed this and showed that there is an increasing tendency, and within each group the numbers are almost the same in the second decimal place. I'll come back to these later on. And then I asked my MSc research student, an adult with 3 children, I told him, make some shapes by cutting paper like children do in elementary school or kindergarten. So he went and did this, but these are shapes that are relevant to mammography, shapes of calcifications and tumors, possibly. Oval, benign, circle, benign, rectangle, no, maybe a blood vessel, triangle, no, this, maybe a calcification, this may be a tumor, this, I don't know, it's pentagon. But it doesn't come in mammograms. So we made these shapes, and the question now is, which one is the smoothest? Easy, circle. Which is the roughest? We said this by visual analysis, and we rank ordered them in this number 1, 2, and 3, and so on. But if I give this list to somebody else, the ordering will be different. So if you want, you can give this to 100 people and then average and say, this is 1, this is 8.2, this is 6.3. You can do that. And then put them through. We digitized them and got the contours and got the compactness. And it's not going in the order 1 to 12. This is smaller. The largest is 0.83, which is 6, which is a rectangle. This one, according to compactness. Is that good? I don't know. It depends on the application. I want this to be maximum for breast cancer detection. This quite likely mammograms will not give me this. So I'm okay. So analyze a number of shapes that are relevant to the application and see which way the ranking goes. The ranking is according to what we did visually using this factor, which will come later. We started at 10 minutes to 2. Is it okay if I go for 2 hours and then take a break? 3 o'clock, 3:45? Okay. Next are moments. Moments are defined for probability density functions, or in engineering for distributions of load. There could be a plate, a structure, a beam, and there is some load on it. You are standing on it or some people are standing. What is the load on that with reference to the support and the area of the beam, the weight distribution? Or it could be a probability density function. The area under the probability density function is equal to 1. And you can normalize any function, fxy. Now we are dealing with two-dimensional functions. Divide by the total sum, so the total sum after normalization is equal to 1. Then you can say it is a distribution, or a density function if you wish. Then you can take moments. It's a two-dimensional function. So x to the power of t, y to the power of q, fxy dx dy. So this is the moment of order pq for a two-dimensional distribution of intensity, density, weight, load, whatever, on a plane, on a plate, on a beam. This could be an image. The values could be the density. And how are they distributed in the xy plane? If they're all equal, you get something. If they're unequal, you get something else. So this is the moment. Now you can define the sequence of moments, MPQ, for PQ going 0, 1, 2, 3, and so on. And there are some theorems, but I'll skip the theorems and mention that you can also get normalized moments, x minus x bar, y minus y bar, to the power of p and q. X bar, y bar are the center of mass coordinates. And they are given by m10 divided by m00, m01 divided by m00. So this is a moment with reference to the centroid. How is the load distributed with reference to the centroid? You can do this for an image too, in 3D if you want. So in a discrete case, you take a moment with the number of pixels you have, sum, it's the same thing. Now you can compute this for a contour. If it is a contour, FMN is equal to 1 on the contour, 0 elsewhere. Or you can also say everything inside the contour is 1, everything outside is 0. So you can do various things. FMN could be a contour, could be a grayscale image, many things. And then there are central moments. There are many of these, you don't have to read this now, but these are called the central moments, and there are combinations. There are some rules that say mu30 is given by this, so you can compute. You have some relationships between moments of various orders. And then you can normalize by dividing by gamma equal to p plus q divided by 2 plus 1. Then mu pq is given as mu pq divided by mu00 to the power of gamma. So this is the zeroth order moment to the power of gamma. It's one way of normalization. There are different ways of normalization again. And then who, in 1971, I think, published a paper giving 7 moments, which he defined like this. Now, I don't want you to read many of these. And Paul also mentioned this earlier. We have used this in many of our projects. For comparative analysis, sometimes they do well, sometimes they don't. But these are purely from statistics-based analysis. And I'm not sure, I have read whose paper, but I don't know the meaning behind this. It's difficult to interpret. And in a given application, I cannot tell you if a malignant tumor should have this high or that low or benign. It's difficult to interpret. Whereas compactness, I can tell you. compactness. The normalized one should be high for malignant, low for benign. Easy. This I simply don't know. I cannot interpret. So the question becomes, do you want statistical measures that you don't care about interpretation, or do you want measures that you want to be able to explain to the radiologist and also yourself to be able to tell, for class A it should be here, class B should be there, class C should be there. These are difficult, not impossible maybe. Then you can take moments of distances to the centroid. I showed a picture earlier. From the centroid you draw lines to all the pixels on the boundary. That distribution of those distances is important. If the shape is a circle, all those lines are equal. So the standard deviation or variance is 0. Whereas if it is a square or if it is a spiculated shape, the variance increases. So moments of the distances to the centroid are useful. What if the moment if the centroid is outside the shape? Then I don't know. I don't know if there is a meaning to that. Whereas if the shape is like this, the centroid is here, I know these lines and it means something, like a moment, bending moment. But if the shape is like a crescent moon and the centroid is outside, why should I take moments with reference to a point that is not in the object? So there are some difficulties sometimes. So for a circle, the variance should be 0. For rough shapes, the variance will increase. And you can take higher order moments. So the moments are dn to the power of p for all n normalized. This is, if p is equal to 1, this is just the mean. And you can take the central moment dn minus m1 to the power of p. And this is, if p is 2, this is variance. And then you can compute various normalized higher order moments. You can take order p moment, central or not, and normalize by the second moment to the power of p over 2. And if p is 3, it is skewness. P is 4, it is kurtosis. So you can get statistics like this of distance to the centroid of all the contour pixels. And these measures have been used in many applications of shape analysis in computer vision. Gupta and Srinath showed this to be useful. They're all invariant to translation, rotation, and so on. How many do you want to go? P equal to 1, 2, 3, 4, 5? I don't know. After some point, any small errors in this will be increased substantially if P is very large. So usually we go up to 4 kurtosis. Mean, variance, skewness, kurtosis. That should be enough for most applications. So sensitivity to noise is the problem. The resulting classifier will not be tolerant to noise. So you have to do some smoothing or pre-processing of the contour before computing these shape factors. You have to remove irrelevant details and artifacts. So these are just the same things I mentioned. Oh, sorry. Now we change the normalization. We tried these shape factors on our test images and found that they were not behaving as expected. So we said, let us change the normalization. Instead of dividing by the normalization factor given earlier, we said we will take, so we divide by m1, m2 to the power of half, this is coefficient of variation. And then m3 divided by m2 to the power of 3 over 2. So this is another way of normalization. So we said we will divide all of them by m1. We took the cube root of skewness. Instead of dividing by standard deviation to the power of 3 over 2, we divide all of them by m1. And we take m4 to the power of 1 over 4. The dimensions are the same, so the result is dimensionless. That's important. So our normalization is with respect to M1 always. And we found that these are better than skewness kurtosis that I explained earlier. And we can also take the difference between the two. We can combine them. So these features are directly comparable. F3 prime is better than F3. This normalization helps. And we combine F3 and F1 and by subtracting and call it MF. And we showed that this is better. Let me go back. Please bear with me. I need to go back to this and show that these numbers have a certain sequence and their behavior within each group is more stable and increasing in this order. So we tested these modified definitions. These are the original definitions F1, F2, F3, and then we changed to F2 prime, F3 prime, combined to MF, and we analyzed this. So we found an advantage, and also in this case, we got these numbers, which I'll show later on, as to how they represent the shapes that we have. And there is another measure that is based on statistics, not of distance to the centroid from the contour, but what are called length statistics. When you have a contour with the vertices here, marked as 0, 1, 2, 3, 4, 5, from every pixel on the boundary, you draw lines to every other pixel. So these are called the chords. And of course, there are duplicates 0 to 4 and 4 to 0, so you don't duplicate. And take all of these, including the sides of the shape, the polygon. So this is the set. And of this set, you get the statistics. This same statistics, mean, standard deviation, skewness, kurtosis, and analyze them. So that has been shown to be useful in some applications. But with all these shape factors, the problem is many shapes may have the same result. So it is not guaranteed to be unique. So many tumors may have the same shape factor, which is not a problem. We would like all malignant tumors to have the same number, all benign to have the same number. No problem. That's all you want to decide. If it is a little more rough, it doesn't matter. So these statistics are also used. I will not go through the equations, they are the same. So let me skip that. And go to Fourier descriptors. Fourier descriptors are important. Not just because I'm from engineering and we use Fourier transform a lot, but there are some ideas here that are not included in the other shape factors we have seen. And there is some intuitive explanation that can be given from the perspective of signal processing. So that comes with electrical engineering. So suppose you have a contour with x and y n points. We form the complex signal Zn equal to xn plus jy n points. Now this is periodic because as you go around, you get the same thing. So this is periodic, and any periodic signal can be analyzed using the Fourier series. What does the Fourier series tell you? It tells you what is the fundamental frequency. It's not important. It tells you are there harmonics. What is the strength of each harmonic? Going round once is one cycle. A sinusoid going once round, and two sinusoids will give you an ellipse. But if the frequency increases, you get rough patterns. So if there are higher order harmonics with large values, amplitudes, the shape is rougher and rougher and rougher. So you can then compute some measures. So the Fourier descriptors are defined as the Fourier transform, capital Zk of Zn, the contour, exponential minus j2 pi divided by n and k. This is the Fourier transformation kernel. 2 pi is divided into n points, number of points on the contour. N is the input index, k is the harmonic index for the output. Here the input is complex. In most signal processing applications, the input is real. If you take my speech, take the Fourier transform. My speech is a real signal. The Fourier transform has conjugate symmetry for positive and negative frequency. Here, the input is complex, the output is complex, but it does not have conjugate symmetry. Given the Fourier descriptors, you can do the inverse Fourier transform, go back and get this. So it is reversible. Or you can modify this. You can filter. You can remove unwanted high frequency components if you don't want. You can make the contour smoother by filtering just like you filter signals. So Zk represents a two-sided complex spectrum, and the index is from minus n over 2 to plus n over 2, minus 1. And there are some important properties. K is the harmonic number in the Fourier series representation. K equal to 1 is a fundamental frequency, is the fundamental frequency. It's a sinusoid in one direction. K equal to minus 1 goes the other way. And that's one period. Zk does not have conjugate symmetry. Zero frequency, what is called DC in signal processing. Z0, 1 over n, average of Z, which is the centroid. So, zero frequency gives you the centroid of the object. If you use Z1 and Z minus 1 and Z0 and go through the inverse, you get an ellipse. Z1 and Z minus 1, each one will give you a circle. I'll show some examples. Z0 is where the circle is located. If you don't want the position, if you want the result to be position invariant, make Z0 equal to 0. High order Fourier descriptors represent fine details or rapid changes. You can rotate a contour. This is given, and you can rotate it by multiplying with exponential j theta. And in the Fourier domain, it's the same thing. It leads to an additional phase component. So rotation is additional phase. If you go in the opposite direction, if you go around a contour this way, you get a certain Fourier transform. If you go the other way, you get Z minus k. Zk, Z minus k will be switched. The spectrum will be switched from positive to negative or negative to positive. If you shift an object, it will affect only the DC component, zero frequency. So Z1 will be Zk, the modified contour will have Zk plus x naught plus jy naught delta k. Only the zero order component is modified. If you scale a contour, the Fourier transform coefficients are also scaled the same way. If you shift the starting point, there is a contour, you start from here, or next time you start from here. What is the difference? If you say Z1 n is Zn minus n naught, Z1k is Zk exponential minus j 2 pi over n n naught k. So it adds a phase factor, which is a linear phase factor. So rotation and shift of the starting point will give you change in phase only, not magnitude. So you can filter the Fourier coefficients, select some coefficients, and then reconstruct modified contours. So we normalized by dividing by, we remove Z0, set it to 0, divide all the coefficients by Z1. So any phase that is present is removed by this in all the coefficients. Then for all the squares, 3 or 4 squares of different size I showed earlier, this is the Fourier spectrum. There are 4, they are all exactly the same. There were 4 triangles, right angle triangles, all of them have the same spectrum. Remember those black triangles and circles I showed earlier? All triangles, all right angle triangles have this. All squares have this, regardless of scaling and rotation. Now this is getting to be a little difficult. I hope you can see. This is the magnitude of Z n. for a benign mass. Can you see that line? I hope you can see that. And this is the Fourier descriptor spectrum. This is for a malignant tumor. It's a different signature, but magnitude of Zn, which is magnitude of Xn plus Jy. This is the spectrum. So you see more energy here in the higher frequency as compared to this one. So as the contour becomes more rough, you get more high frequency. If you filter the contour, you get smoother contours. It's difficult for me to see this even here. This is the contour, and if I use Z1, I get this circle. If I use Z minus 1, I get this circle. If I combine, you get this oval. The contour, it's very difficult to see, is there. And if I use 7 coefficients, I get this representation of the contour. It's a filtered contour. So the original and the filtered contours are shown here. I can get a smoother contour by selecting only the low frequency components and remove irrelevant detail. The same here. The contour is a rough contour of a malignant tumor. It's very hard to see there. Using Z1 and Z minus 1, I get 2 circles. Using both of them, I get this ellipse. If I use 21 coefficients, I get this contour. If I use 41 coefficients, I get this contour. The original contour was shown earlier, the malignant tumor. But these are filtered versions. Are they useful? I don't know. It is one possibility. In the analysis of contours of tumors, filtering is not important. There is no need for me to show the radiologist a filtered version of the contour drawn by the radiologist. That's not important. We want to convert the Fourier spectrum into one number. The Fourier spectrum has a number of complex values, as many values as the input contour. How many of them should I use for pattern classification? I don't know. Can I reduce it to one number? Maybe. So we divide the spectrum by Z1 to normalize for size and remove effect of starting point and rotation. Remove Z0, the centroid, to remove the effect of shift. The magnitudes are independent of position, size, orientation, starting point of the contour after this. So we take only the magnitude. The normalized Fourier descriptors, 0 for k equals 0, zk divided by z1, and then we define a Fourier factor as 1 minus this quantity. Z naught k divided by k. We divide, if you multiply, the high frequency noise is increased. So instead we chose to give decreasing weight with frequency. Divide by the sum of all the Fourier coefficients magnitude. Because this will decrease with rough shapes, we took 1 minus that. So this number now increases with increasing roughness of shape. So this is what we proposed. It is limited to the range 0 to 1. So
I'm
it's,
sorry.
Yeah.
To understand better. So you take all the coefficients
yes,
and you
Z0
sum all of
k.
them. Okay, you sum all of them, divide by the.
If they're normalized, divide by Z1,
Okay.
and then you take the magnitude and divide by k, and normalize by the total. This is like total power. We're not squaring, that's all.
So to interpret it again as number would be bigger if it's more rough? No. Yeah.
After this, 1 minus that.
Okay.
1 minus this quantity, the number is bigger if it is rougher. So this is what we wanted. So let me go back to that table. Please bear with me when I run back. Yep. So here, the Fourier factor, all of these have the same, almost the same number. A little variation here, almost the same, increasing. And more importantly for this, the numbering we did was 1 to 12 like this. And the Fourier factor increases in this order. So this increasing order, we believe, agrees with the way we were thinking. Whereas compactness says this has maximum. To us, this is maximum roughness. So depending on the application, you have to define what is the sequence of roughness. Compactness says this is the maximum roughness. Fourier factor says this is the roughness. And in mammography, this is important. This is more high frequency than that. So it is good to have multiple. I'm not saying use only one. So I'll show all these three together at the end, based on compactness, moments, Fourier factor, but their sequence is different. Only the Fourier factor agrees with this ranking that was according to our judgment. So, no, don't see that. That comes later. Don't look at that. Okay, compact. Okay, that is done. Fractional concavity I already explained, so I will skip this. I already gave this example. The last shape factor that is relevant in mammography is analysis of speculation. I've explained speculation, I showed some examples, I'll show some more. So invasive carcinoma, cancer due to nature of infiltration, will form narrow. The previous terminology was stellate. They were called stellate tumors, like stars. But because stars are beautiful and tumors are not beautiful, it was changed to speculated. So sometimes I have used this word, which I should change. So we proposed a speculation index. We wanted the number to increase if the contour had more spicules and narrow spicules and long spicules. So these are the considerations in the design, in discussion with the radiologist. So I will skip the text. I'll show the picture here and then come back. So here is a contour of a malignant tumor. And these are points of inflection with a plus mark. These are the open circles, are the vertices of the polygonal model. So we use the polygonal model, we keep the points of inflection, and we say in between 2 points of inflection, that is SPQ. It may not be SPQ, this is between 2 points of inflection. We say, okay, we will analyze that also. They're not throwing anything. We will analyze every part of the contour between 2 points of inflection. In between, there are many points of the polygon. So this is not a straight line. So how do you account for measurement of the angle of the spicule? So we said, if this is a point of inflection and this is another point of inflection, this is a spicule, not a segment of the contour. If you don't want to call it spicule, it's a segment. And if there is only one vertex in between, there are only 2 sides and only one angle, no problem. So number of sides is 2, theta is theta 1, that's all. But if it is like this is SPQ, this is the point of inflection, another point of inflection. Now 1, 2, 3, 4, 5 sides. Length of the spicule, easy, add the sides. Angle, what is the angle of this? You can do various things, you can fix some triangle or something. But we said we will analyze all the angles inside. There are 4 angles. We take the average of the angles and call it a threshold. And take only those angles that are less than the threshold. And average those and say that is the angle of this spicule. In this case, theta 2 plus theta 3 over 2. These are very large angles. So, like that. So we don't want to include them. So this is how we get the length of SPQ. Okay, just the sum of all the sides, no problem. Angle, a little bit of processing. So this is the definition. The rest of the text we can ignore. And then the speculation index we defined in this manner. The sum of all the spicule lengths how many other spicules you have, capital N, not the number of pixels, but spicules. Multiply that with a weighting factor 1 plus cosine theta n. There was no need to add 1, but we did. If it is a very narrow spicule, theta is small, cosine theta very large. So this weight increases when the angle is small. The weight increases when the spicule is long, and normalized by the total length of all the spicules, which is the perimeter of the whole contour. So we analyze all segments, even if it is almost straight. And if it is almost straight, 180 degrees, that will be 0, so it doesn't matter. So we're not selecting, we will let the angle take care of the weight. So 180 degrees, almost straight line, this will be -1, so it is 0 for that spicule. It's not a spicule, like this. This will not contribute much to the speculation index, these two will. But then the total length is taken into account. So this is another measure that we define particularly for analysis of breast tumors in mammograms based on the discussion with the radiologist. So this is very particular to radiology. One of my students in India has extended this to lung nodules in 3 dimensions. So you need to get all of this in 3D. So it is possible to do some of this in 3D. So let me give you 2 examples to close this. Shape analysis of calcifications. Malignant calcifications usually appear in large clusters, meaning many small specks of calcium deposit within a small area, and they have rough shapes. Whereas calcifications associated with benign conditions are generally large and round. I don't understand this. It is said to be said this way, but of course they are not born being large. They have to start small and then they become large. So if they are large, it means they have already been growing for some time. But this is how it is defined. But if calcifications are very small and there are many in a cluster, the radiologist immediately says, go for a biopsy. Shape is important in discriminating between this. I don't have the shape of calcifications in this chapter, but if you download my lecture notes for all of the preceding chapters, you will see examples. My book is not available for downloading, but my lecture notes with all these equations and all the figures and all the tables in the book in this format may be downloaded from my website. So you can see examples of calcifications in the segmentation chapter. I'll show masses here. So in this 3-dimensional plot, we have compactness, the Fourier factor increasing this way, and the moment factor going this way. Benign calcifications here, malignant calcifications there. Compactness is doing very well. So put a threshold here and get a good result. But this is 3D, so you can rotate and you get different projections. The statistics, how many? 143 calcifications, 79 malignant, 64 benign. This is moment. There is some overlap. Fourier factor, not bad. Mean and standard deviation. Compactness, very good separation. So it's beautiful, it works very well for calcifications. We did this with both automatically detected contours and manually marked contours. Now, these are manually drawn contours of breast tumors in mammograms, benign masses and malignant tumors combined. We have 2 data sets, this is one, and we have rank ordered the contours. The actual contours are of different size. They have all been plotted to the same size here. What is marked as B is benign. What is marked as M is malignant. And these have been arranged in the increasing order of magnitude of the feature vector, compactness, Fourier factor, speculation index. 3-dimensional, take the magnitude, x squared plus y squared plus z squared square root. So this is the smallest number, almost a circle. So as you come, there's more roughness. And very rough. And I don't know about this one. This is very rough, but I don't know why this came in. And this is benign. Most of the benign ones are here. All of these are benign. Most of the malignant are here. But in between, there are some benign that are rough, some malignant that are not so rough. So we were so happy with all our equations and test objects. And when we saw this, we sort of went crying back to the radiologist and said, what is this? And he said, these malignant tumors did not read the textbook. So, why is this malignant tumor not rough, more rough? I don't know. Why is this benign one so rough? It could be a mistake in biopsy. That's what Dr. Desatel said. He said, those who prepared the database, they didn't do the contour. Dr. Desatel drew the contours. He said, the database says this is benign, but I'm not so sure. That's what he said. But that's what the database says. But this is the way things go in real life. Biological entities don't obey rules. Engineers obey rules. Computer scientists also, I think. Sometimes. But engineers obey rules. Mathematical objects, computer-generated objects obey rules. Objects manufactured by machines are precise. All the square things are there, all the round things are here. But when something comes from a biological system, there is variability. We are all normal people, but we look very different. Our shapes are different, and we are all still normal, healthy people. So there is a wide range for normal, and a even wider range for abnormal. So in between there is overlap, as both Dr. Leticia showed yesterday and Dr. Paulo showed today. There is overlap between the classes. There is some confusion. You will not get 100%. So this is the three-dimensional plot. Most benign here, most malignant here. Some benigns are here, some mixture. So the accuracy is not 100%. Why? This is based only on shape. Texture is also important. Density is important. Grayscale variation is important. You bring all of them together, perhaps you get better than this. But this chapter is only on shape, so this is only shape. So, shape analysis requires the contours. Obtaining a contour with good accuracy is difficult. I said could be in the book, but it is difficult. For you to write a computer algorithm to segment every object in this and get every chair and every table, it's not easy. For somebody to go and draw this by hand is very tedious, and there will be some error, some distortion. In clinical practice, it is not common to draw. Sometimes they do, but when you ask a radiologist, please draw me the contours of 1,000 masses, he will never come to your office again. But Dr. Desatel has been very kind, and we have been collaborating for a number of years. I'm very fortunate. Malignant tumors exhibit poor definitions of their margins. They are ill-defined. So how do you draw the contour? There is no contour. There is no boundary. It is your imagination. Yeah, there should be something there. So identifying and drawing their contours is difficult for a radiologist and for a computer. And these contours could have artifacts and noise. They will corrupt the shape factors. There could be significant variation between the contours drawn by different individuals for the same objects. And what is rough for you may be smooth for me. Not too often, but at least the ranking of roughness will be different. And the contour of a 3D entity like a tumor as seen in a 2D projection image as in a mammogram is not perfect. It doesn't lend for perfect analysis. So you have to go to 3D. You cannot go to 3D imaging for the breast because of radiation concerns, but for the lung nodules and brain tumors and others, you can get 3D boundaries and do most of this in 3D. And then perhaps the results will be better. this I mentioned the contours of biological entities. There is significant overlap, subjective artifacts of various types I mentioned. The inclusion of measures representing other characteristics, texture, gradient, sharpness, can complement and perhaps improve the accuracy of classification, but that is the next chapter. So thank you, and we will take a break here. 15 minutes? Yeah, and we'll come back at 4 o'clock. Thank you. This is the surface of the